Ladies and gentlemen, welcome to video 2 where we look at the D1 graph theory. So most of this is about definitions, and these definitions need to be learned because they can and will be asked during your exam papers. They ask for the definitions. I've created a little blue kit over here if you want to give that a go and see where you're at, and then pick up and go over the ones you're not so sure about. Then that would be an effective way to do this. I will, however, talk through the terminology and definitions. Let's begin. So first up, what is a graph? A graph is a collection of vertices and edges. It's just a general term. So all of these things on the right all of these things on the right are graphs because they have vertices, which are the dots, and edges, which are the lines and the curves in between. These dots have two different names. They could be called a vertex, plural vertices, which you can see over here, or a node. Both are interchangeable definitions. It can be where edges meet, your node, or it can just be flying over here in the middle of nowhere. Doesn't matter. If it's a dot, it's a node. These edges can also be called arcs, and an arc is a connection between two vertices. So this is a node. Oh, hang on. This is a node. That's fine. This is not an edge. Why not? Because it doesn't connect two nodes. Now it does. Now it becomes an edge. So you can't have your lines flying off into the ether. It must connect the edges. The arcs must connect two nodes. A tree is a graph with no cycle. So a cycle is a way to get back to the start. So currently, no cycles. We're good. Now we have a cycle, not a tree. Even if we have something over here and something over here, in our graph, if there is a way to start at a node and travel around a small area of it and get back to that node, we have created a cycle. As you can see, the path in yellow, so therefore it is not a tree. So if you look at the three graphs we have here, we have a cycle here, we have a cycle here, or we could have had this as a cycle. Lots of cycles. What about this one? Yep, we've got a cycle, we can travel around. We've got a cycle here, we've got a cycle all the way around. All of them work. And again, cycles everywhere. What about here? Once we travel, we can't get back. Oh no! So that is a tree. Here we also have a tree. It's just, so the word we use, and this will come up a bit later, is isomorphic. And isomorphic graphs are graphs which look different but are essentially the same. So if you look at these two graphs, this is just a node with one connection, two connections, one. And this one, 1, 2, 2, 1. These two are isomorphic. This one has 1, 3, 1, 1, not isomorphic. So isomorphic is just the same information displayed in a slightly different style. Any graphs which are isomorphic, so in a mark scheme, they might have one diagram. Your diagram might look differently. They're both right. Isomorphic graphs, as far as you're concerned, will get the marks. So if your graph looked like this one or like this one, doesn't matter. They are isomorphic. Okay. The order, or sometimes called the degree of a node, is the number of lines going into it, or think of it as the number of exits. So on some questions, it's quite straightforward. This node here, we have two ways to get out. So this has a 2. This one has 3 ways out. 3. 2, 3, and this is normally how we would label if we came to it. 2, 3, 2, 3. Okay, easy, right? You can't get that wrong. Unless things are a little bit vague. Let's look particularly at this node here. how many ways out do we have? Well, that's one, I think we can agree, and this is another one, I think we can agree. But this goes back in, so does that count as 1 or 2? Well, the answer is not to look at where the paths are going, but just to focus on the node itself. So if you remove everything else and just look at what's in the box, your node has 4 exits. So the valency or the order of that is degree 4. Okay, so don't overcomplicate it. So for this graph, this would have a valency of 4, 3, 3, 0. Okay, a simple graph has no loops or multiple edges. So this is what we call a multiple edges, 2 different ways to go from one node to the next. Here we have loops, yep. So this is what we mean by a loop, a way back to the point exactly. This is a loop. Multiple edges, these are multiple edges, so this is not a simple graph. There are no loops in this graph here, and there are no multiple edges between the same 2 nodes, and the same is true here. So these 2 graphs you would say are simple. If there was a line going from here to here, we now have 2 routes from this top left node to the bottom right node. So therefore this now would not be a simple graph. The word simple is I don't like it. It's not very nice because the word simple itself doesn't tell you, or it's not evocative of what the question's asking for. So that again is something you need to be comfortable with, you need to know. A path is a route from one vertex to another which does not repeat any edge. So imagine you're walking across, I don't know, drawbridges of ice or something, and as you walk across them they collapse. That's what a path is. You're going from one vertex to another and you don't repeat any edge. So if you went from here to here, let's plot this out, and then we went from here to here, and then we went back here. Okay, now we can't go any further without repeating an edge. So that itself would be a path. A cycle is a route. So look, it's a route from one vertex to another which does not repeat any edge. A cycle is a route starting and finishing at the same vertex. So this is a cycle. Let me just get rid of these. So this is a cycle. This is a cycle. This is a cycle. And whoa, all of that together would also be a cycle because we're starting and finishing at the same vertex. Connected graph, it's a specific term. A connected graph is there's a route from each vertex to any other vertex. So we have a terminology we use for connected graphs using K. So K2 would be 2 nodes which are connected. K3 would be 3 nodes. Each node is connected to every other node. K4, 4 nodes. Is that connected? No, it's not. Every pair of nodes must be connected. Now it's connected. You can go from each one now, has a valency of 3 because it connects to the 3 of the other nodes. And K5, so pentagram, and we connect. So because you have 5 nodes, each node must have a valency of 1 less 4, because that's how you know it's connected to each one of the other 4 nodes. So you can do a little counter and a check to make sure you have that situation. Okay. So that's what connected graphs are. Complete graph. Oh no, sorry, my mistake. All of these are complete graphs. Connected just means you can get from anywhere to anywhere else. See, even me tripping up on the definitions. Gotta revise this. I might do a blue kit. So connected graph means you can get from any node to anyone else. Now there is one of these given graphs which shows a graph which isn't connected here. You can go from here to any of the other nodes. You can get eventually, even if it's not direct through a node, that's fine. But there is no path from any of these three nodes to get to our stray over here. So this graph, you would say, is not connected. If consider each of these nodes as maybe centers of travel. So let's say airports. That airport has no flights coming or going, so there is no way to get there. A bipartite graph. Now, I'm giving you the definition for bipartite. It doesn't actually fall within our course, but if you're doing questions from the previous spec, it will come up. So I just want you to know what one is. So a bipartite graph is where the vertices are in two sets. And it looks kind of like this. So you have, let's say you were connecting students on the left to subjects they love, then this would be a bipartite graph. You notice there's no way to connect Alan and Betty. Basically the connections are made across the group rather than between the group. You know, in biology to English, no connection. But biology is done by Chris and done by Alan. So you can see that. And that's what bipartite means, right? Bi, two, partite, two parts. A planar graph is one which can be drawn with no edges crossing. So you see this over here? That's a planar graph. If I'd done it like this, you would say, oh, there are edges crossing. So can we make it planar? Well, if we take this edge here and kind of unwrap it and write it on the outside, now it's a planar graph. There are no crossings of lines and paths. Subgraph is a small group of a graph taken from a larger graph. Now, it's important that, so if we look at this as a graph, what are the possible subgraphs? Well, that's a subgraph. That's a subgraph. That's a subgraph. That's a subgraph. All of these are just parts of the actual graph. There are 6 parts to this graph. There are the 3 nodes and there are the 3 edges. Okay? So there are 6 parts, and if you remove any one of them, then you make a subgraph. Now, your Hamiltonian cycle is a cycle that visits every vertex. So, you know, think of it like, I don't know, the play Hamilton went to every state of the United States. It went everywhere. It went to every node. So the Hamiltonian cycle visits every vertex. It doesn't talk about the paths. It's only interested in the nodes, the vertices. Then we've got a Eulerian cycle. So a Eulerian cycle is the opposite of a Hamiltonian. Let's say your Eulerian cycle is you need to paint all the roads in a town. It doesn't matter where the roads meet, you have to travel down each road. So a Eulerian cycle is a cycle that travels along every edge of the graph. A Eulerian graph is a graph which has no odd vertices. Now that might seem a bit weird, but that comes in a later unit when we talk about Eulerian and semi-Eulerian graphs. So a Eulerian graph has basically every node is even. A semi-Eulerian has 2 odd. So if you look at our graph over here, we have 1, 2, 2, 1. This is a semi-Eulerian. 1, 2, 2, 1. Semi-Eulerian. 1, 1, 1, 3. All odd. It is not Eulerian. What about these up here? Write your nodes down, count them carefully. It's really easy on the more complex nodes to miscount, so be careful. This one is semi-Eulerian. So we have 2, 3, 2, 3. So if you look at these, the order, if you go around, is 2, 3, 2, 3, and the order here is 2, 3, 2, 3. That's one way of checking whether graphs are isomorphic. If the same nodes, as you move around the graph, have the same valencies, then that's one way of checking. So if you look at this one over here, the valency of this, is it 3, is it 4? We have a loop. What do? We look at the node. 1, 2, 3, 4, 4, 3, 3, 0. Is 0 an even number? I don't know. You guys can think about that. You can debate it in the comments underneath. But for now, this one is no odd vertices. So 2 odd vertices. So semi-Eulerian? Is it? Nope. The graph needs to be connected. So this 0 over here stops it being semi-Eulerian. Okay, a digraph is just where you have arrows. So if we put an arrow here, how would that change the valencies of these nodes? Well, let's do the easy ones. This one still has a valency of 1, a valency of 1. This one has 2 exits. This one now only has 1 exit. So although there are 2 lines connected to it, only one of them can be traversed. So the valency of this node would be 1. And an incidence matrix is a matrix which represents the edges in a graph. So the incidence matrix of this, if we look at it, what does A connect to? There's 1 connection to B and 1 connection to C. That's what the first row tells us. What does B connect to? It connects to A, connects to C. 1 connection, 1 connection. What does C connect to? Connects to A, connects to B, and there are 2 paths to itself. So the valency of C is 4, so the numbers here should add up to 4. If you think, like I said, 1, 2, 3, 4. There are 4 connections. 2 of the paths lead back to C, 1 to A, and 1 to B. Okay? Excellent. We'll leave it there for now. If you have any questions, stick them in the comments below.